Today we are going to study directional overcurrent protection. No, again, see the overcurrent protection can be given directional feature by adding directional element in the protection system. Basically, see directional overcurrent protection responds to overcurrent for a particular direction flow. If the power flow is in the opposite direction, the directional overcurrent protection remains unoperative. Okay, so in other words, I'll say these directional overcurrent relays are responding to the overcurrent for a particular directional flow. Now again, the directional overcurrent protection comprises one overcurrent relay and a power directional relay in a single relay casing. Okay, so I repeat, the directional overcurrent protection comprises one overcurrent relay and a power direction. It can be either an overcurrent relay or it can be a power directional relay in a single relay casing. Okay, so the power directional relay does not measure the power but is arranged to respond to the direction of the power flow. Means you understood that. So with directional overcurrent protection comprises an overcurrent relay and a power directional relay in a single relay casing. So power directional relay does not measure the power but is arranged to respond to the direction of the power flow. Again, the directional operation of the relay is used when the selectivity can be achieved by directional relaying. Okay, so I repeat, see, directional operation of the relay is used where the selectivity can be achieved by directional relaying. Basically, see, the main feature is that, see, these directional overcurrent relay, it recognizes the direction in which the fault occurs relative to location of the relay. It is set such that it actuates for the faults which are occurring in one direction only. It does not react for the faults which are occurring in the other direction. Now consider a feed. You just look at this diagram over here. Consider this entire feeder XY as shown in the figure. Okay, as you can see, students, this feeder XY is passing to section A over here. It's passing through the stage substation A. Now the circuit breaker. Now again, see the circuit breaker in AY, that is CBY, is provided with the directional relay R. Okay, and which will trip if the circuit breaker CBY if the fault power flow is in direction A only. So as you can see over here, it's mentioned here, this arrow mark indicates the direction of tripping over here. So as you can see, see the circuit breaker in the feeder AY-CBY is provided with the directional relay R. Now again, this is the main direction of tripping. Now this relay R is going to trip the circuit breaker CBY if the fault power flow takes place in this direction of A only. However, if suppose the faults take place in this feeder AX, the circuit breaker CBY does not trip unnecessarily. Means if the fault is taking place, suppose if the fault is taking place in this section of the fader, then this circuit breaker CBY will not it does not trip unnecessarily. However, for the faults in the fader however, when the fault is taking place in the fader AY, the circuit breaker CBY trips. Okay, I repeat, however, the faults in the feeder AY, the circuit breaker CBY trips because its protective relaying is set in such a directional feature to act in the direction AY. Okay, so I repeat, so means for the fault, since if it means if the fault is taking place in this particular feeder AY, the circuit breaker CBY will trip because it's a protective relaying. Because the point C, I repeat once, if all the feeder AY, the circuit CBY trip is said to direction act in direction AY only. Because CBY trip, because the protective relay is there, is set to the protective relay is set to the directional feature. This relay is set to direction to act in this direction AY only. Okay. So this is about directional overcurrent protection. Now another interesting example of directional protection is that of reverse power protection of the generator. That is, you just look at this diagram. This is a diagram showing reverse power protection of generator. Suppose if the prime mover of generator fails, okay, I repeat, if the prime mover of the generator fails, the generator continues. The generator continues to run as a motor and takes the power from this particular bus bar. Means if the prime mover fails, so if the prime mover fails over here, if the prime mover is failing over here, generator continues to act as a motor, thus taking electrical input from the bus bar, and thus in other words, I will say this is a directional flow trip, and thus this reliable trip. Now, directional power protection operates in a member in accordance with the direction of the power flow. Okay, so I repeat, directional power protection operates in direction of power flow, whereas this reverse power protection, it operates when the power direction is reversed in relation to the normal power flow. Okay, so I repeat, directional power protection operates according to direction of power flow, whereas the reverse power protection operates when the power direction is reversed in relation, means when direction of power is reversed in the relation normal power flow, and reverse power flow is different in construction than the directional over current relay. Next is directional earth fault protection. Now basically see, in the directional overcurrent protection. Okay, I repeat, in the directional overcurrent protection, the current coil of the relay is actuated from the secondary current of the line cities, whereas the current coil of directional earth fault relay is actuated by the residual current. Means what is saying, that if in directional overcurrent, the current coil of relay is actuated on the current coil of the relay is actuated on secondary current of line cities, whereas the current coil of this whereas the current coil of directional outward relay is actuated by the residual current. Now, in directional overcurrent relay, see, in directional overcurrent relay, the voltage coil is actuated by the secondary of the line VT. Okay, so I repeat, directional overcurrent happens. The voltage coil is actuated by the secondary of line VT. In directional earth fault relay, in directional earth fault relay, yeah, the voltage coil is actuated by the residual voltage. Now again, see, this is a directional earth fault relay senses the direction in which the earth fault occurs with respect to the relay location. No, okay, the actual outward relay senses the direction in which the outward occurs is to the relocation, and it operates for fault. Again, since I told you the name is directional relay, so it operates for the fault in a particular direction. Now again, the directional earth fault relay single phase unit has two coils. The polarizing coil is obtained either from residual current, that is IRS equal to IA plus IB plus IC, or residual voltage VRS equal to VAE plus VBC plus VCE, where VA, VB and VC are the phase voltages. Okay, repeat this here. Directional outward relay single phase unit has two coils here. The polarizing quantities obtained either, this is a polarizing quantity is obtained either residual current IRS, that is IA plus IC, or residual voltage VRS, VAE plus VB plus VC, where VAE, where these terms, I just one minute, let me put on, yeah, where these terms you can see VAE, VBE and VC, they are the phase voltages. Now again, see, look at the figure 27.14. So this is the connection of the directional earth fault relay over here. So as you can see, students, this structure, this is nothing but the directional earth fault relay. Again, for this topic, you have to refer SS Rao chapter number 27. Again, referring to the figure, the earth directional earth fault relay has two coils. One of the coil is connected in residual current circuits. Okay, so see, I'll show, I'll have a diagram. I'll show. So you can see over here, this directional earth fault relay is having two coils over here. Okay, one coil is one of the coil is connected in the residual. Yes, anybody wants to speak something? Okay. Now again, you can see, you see this is RS output relay. So one of the it is two. You can see this relay is having two coils over here. One coil is connected in residual current circuits. Okay, so see this coil gets current outfall. So other coil gets this other coil. This coil, the coil is getting a current outfall currents. There is a IR2 over here. This coil you can see. Where this coil, see this coil is getting current current outward over here. Whereas the other coil you can see this other coil is getting this other coil is getting residual voltage. So VRS equal to VAE plus VB plus VCE. Okay, so other this coil is getting residual voltage over here. So this where VRS is VAE plus VB. Again, what is VAE? I told you VAE, VB, and VCE. They're the secondary voltage of the potential transformers PT. Okay, VAE. VAE are very difficult. 10, 17. VAE. VVC, secondary voltage of potential transformers. Yeah. Again, the three-phase five-limb potential transformers are there. Yeah. Again, three-phase five-limb potential transformers are three single separate single-phase PTs are connected as shown in figure 2714. Again, the three-phase five-limb potential transformer or three separate. Yeah, see three-phase five-limb potential transformer. As you can see over here, you can see these are, let me present these CTs over here. Okay, and these are PT. These are the potential transformers in the picture. You all can see very well. So either it can have three-phase five-limb potential transformers. It can have, or you can have a three single-phase potential transformer, three separate, or you can use a three separate single-phase potential transformers are connected. The coil which is connected in potential in the secondary circuit, it gives a polarizing field to this directional earth fault relay. Whereas if we look at this directional current IRS over here, let us look at this residual current IRS. This residual current IRES is basically out of balance current is given to the current coil. Okay, I repeat, the residual current IRES, that is out of balance current. IRES is out of balance current, is given to the current coil here. And this residual voltage V, you can see this is the residual voltage over here. This residual voltage VRES is given to the voltage coil of the relay. So basically, see the torque, the operating torque you can see is proportional to IRES. The operating torque is proportional to IRES into VRES into cos of phi minus alpha. Okay, torque T is equal to IRES into VRES cos of phi minus alpha, where phi is basically the angle between the residue IRES and VRES. That is, phi is the angle between the residual current and residual voltage, and alpha is the angle of the maximum torque. Okay. So this is all about the directional over this till now. So all about directional overcurrent and the earth fault relay. Next is, let us go to differential protection. First, let us try to understand what do you mean by the word differential protection. Basically, see, as the name indicates, differential protection. Again, for this topic, I would refer SS Rao chapter number 28. A differential relay responds to the vector difference between two or more similar electrical quantities. From this definition, following aspects are known. Okay. Again, the differential relay has at least two actuating quantities, say I1 and I2. Again, two or more actually, I repeat again. So, on this definition, the differential relay has at least two actuating quantities, I1, I2. The two or more actuating quantities should be similar. That is, it can be current or it can be current. Again, the relay responds to the vector difference between the two, that is I1, I2, which includes magnitude or the phase angle difference. Is it clear to everyone? So basically, see, a differential word response vector is related to almost similar electrical quantity. Okay. So from this definition, the following aspects are known. So basically, see, the differential relay has at least two actuating quantities, say I1 and I2. Now again, the two or more actuating quantities should be similar, that is current or current. Now again, the relay responds to the vector difference between the two quantities, that is I1 minus I2, which includes when I say vector difference means what? The term vector difference includes both magnitude or the phase angle difference. Okay. As I1 and I2. Now the two of them actually should be similar. If the two actual quantity has to be similar basically. So what is this a difference relate what responds to the differential response to response to vector difference between the two or more similar electrical quantities. Just 1 minute, let me carry the charger. Now again, see the differential protection is generally, uh, oh, the differential protection is generally unit protection. Yeah, so the protected zone is exactly determined by the location of CTs or the VTs. Okay, so I repeat, the differential protection is generally unit protection. The protection zone is determined by the location of CT or the VT. Now again, the vector difference is achieved by suitable connection of CTs or the VT secondary. Now, when I say vector difference means I told you it's a magnitude difference ho sakta hai, as well as it can also be the phase angle difference. That is achieved by suitable connection of current CT, a transformer or voltage transformer secondaries. Now again, let us look at the main principle of the differential protection. Now again, see, most of the differential relays are current differential relays. Okay, let me tell you the means application first, then I'll go to principle. Most of differential relays are current differential relay in which the vector difference between the current entering the winding and current leaving the winding can be used to sense for sensing and the relay operation. Means most of relays are this is current differential relay in which the vector difference between the vector difference of current entering the winding and current the vector difference between the current entering the winding current leaving the winding is used for sensing and relay operation. Now again, the differential protection principle is used in following application: protection of generator, a protection of generator transformer unit. Now, okay, it can be used as protection of generators, also or it can be used as protection of combined generator transformer unit, protection of transformers, protection of feeder by pilot via differential protection. Now again, protection of transmission lines by phase comparison carrier current protection, and protection of large motors, and this we have the bus zone protection. Okay, now so first protection of generators, the general transformer per protection unit, the protection of transformers, we have protection of feeders, so we have a pilot wire differential protection, the protection of transmission line by phase comparison carrier current, and protection of large motors and the bus zone protection. Next is let us now look at the principle of circulating current differential Morse price protection. Okay, principle of circulating current differential, that is Morse price protection. Now figure 28.1a illustrates the principle of differential protection of generators and the transformer. Okay, so I will figure this figure. Let us look at what figure 28.1a. So this one you can see this figure indicates a principle of the circulating current differential protection. Now, as I told you, this is also known as a Morse price protection. For let us try to understand. Now, where X, okay, let me zoom it here. Where X is the winding of the protected machine. Okay, means you can see you can see over here this X you can see this X is the winding of the main protected machine over here. Okay, and basically, see, when there is no internal fault, the current entering the protect and the current which is entering the protected winding is that is X. Let us say it is labeled as X over there. It is used for is equal in phase and magnitude to the current leaving the protected winding X. Now again, the CTs are of such a ratio that C means the CT ratios are in such means the CT ratios are in such a way that means during normal conditions or for external faults, that is through fault, the secondary current of CTs are equal. So these currents, say I1 and I2, they circulate in the pilot wires. So the polarity connections are such that I1 and I2, I repeat, see the polarity connections are such that the I1 and I2 circulate in the pilot wires. Now I'll tell you what, first I'll show you what are the pilot wires first. So as you can see over here, see these are wires are called as the pilot wires. I'll show it over here. Yeah, see these two wires are called as a pilot wire basically. So I1, I2 circulate in the pilot. The polarity connections are addressed in such a way that the currents I1 and I2 are in the same direction in the pilot wires during the normal conditions or during the external faults. Now the relay operating coil means, as you can see in the figure, this is a relay operating coil. This relay operating coil is basically connected in the middle of the pilot wire. Now this relay unit is basically overcurrent type. Students, so during the normal condition, during normal conditions and the external fault, yeah, the power protection system is balanced. Okay, I repeat, during normal conditions, in normal conditions and the external faults, the protection system is balanced and the CT ratios are in such a way that the secondary currents are equal. So I repeat, see, during the normal conditions and the normal condition external fault, yeah, the protection system is the system is balanced and the CT ratios are in such a way. As I repeat, in normal condition external for the power protection system is balanced, yeah, and the CT ratios are in such a way that the secondary currents are equal. These two currents circulate in the pilot wires. Again, the vector differential current I1 minus I2, which flows through relay coil, is zero. So I repeat, during normal condition external fault, the power system protection system is balanced here, and the CT ratio current in such a way that the secondary currents are of the CTs are equal. Okay, what happened? Somebody, what happened? Any problem to anyone? Students? Somebody like, okay, so when I1, the vector differential current I1 minus I2, which flow through the relay coil is zero. Okay, so means what happens? I repeat once again. See, during normal condition external fault, see the powers, protection system is balanced, and the CT ratio current is such a way that the secondary currents are equal. Yeah, these currents circulate in the pilot wires. So vector differential current I1 minus I2, which flows through the relay coil is zero. Yeah, the vector to which I1 minus I2 which flows through relay coil I1 minus I2 is equal to zero. That indicates normal condition of the external faults. Okay. So this balance is restored for the internal faults. So means when the means how the balance is destroyed. Let me tell you. So when the fault occurs in the protected zone, the current entering the protected winding is not equal to that current leaving the winding, because some current flows to the fault. The differential current I1 minus I2 flows through the relay operating coil, and the relay operates when the operating torque is more than the restraining torque, and the currents I1 and I2 circulate in the secondary circuit. Hence the CTs does not get damaged. The polarities of CTs are considered. The CTs are cut in such a way that the circulating current I1 and I2 are as shown. Now, what are the main difficulties in differential protection? Now again, students, this has been asked in the university examination of what are the main difficulties in the differential protection. First is difference in the pilot wire length. Now, difference in pilot wire length. See the current on the CTs and the machine to be protected are located at the different size, and normally it is not possible to connect the relay coil to the equipotential points. Okay, so I repeat, the current transformer CTs and the machine to be protected are located at different sites basically, and normally it is not possible to connect the relay coil to the equipotential points. And this difficulty is overcome by connecting adjustable resistors in series with the pilot wires. Okay. So I feel the CTs and machine point look at different sites are located, and it's not possible to connect the relay coil to the equipotential points. The this difficulty is overcome by connecting adjustable resistors in series. Second is the CT ratio errors during short circuit. Now, basically, the current transformers may have almost equal ratio at normal currents, but during the short circuit condition, the primary currents are unduly large. Okay, the ratio errors of the CTs on either side differ during these conditions due to inherent difference in CT characteristic arising out of difference in the magnetic circuit. Now, there can be when unequal DC components in short circuit currents. And third one is saturation of CT magnetic circuit during short circuit condition. Means during the short circuit saturation of CT magnetic circuit. So due to these causes, the relay may operate even for the external faults. Means when there is saturation of the CT magnetic circuit during CT, means the CT magnetic circuit gets saturated, and this relay may operate for external faults. Relay may lose its stability for through faults. And again, to overcome this difficulty, means if suppose the CT magnetic circuit is getting saturated, then to overcome the difficulty, we go for percent differential relay or biased differential relay is used. Is essentially a circulating current differential relay with additional restraining coil. The current flowing in restraining coil is I1 plus I2 by 2, and the restraining current. So let me show a diagram over here. See this one. You can see over here, this is called the percent differential relay, and additional coil, restraining coil is used over here. The percent differential bias differential relay is used. It essentially is circulating current, yeah, circulating current differential relay with additional restraining coil. So the current which flows in that restraining coil, you can see, is proportional to I1 plus I2 by 2, and means as you can see, this is the restraining coil. Actually, you can see यहाँ पे I1 current flow हो रहा है, I2 current flow हो रहा है. यहाँ पे ये जो current flow होता है, that's called basically I1 plus I2 by 2. Okay. By do, and the restraining current prevents the operation. This restraining coil is going to prevent the operation during the means it's protecting from the mal operation of the relays during the external faults. Because what happens, see, with the rise in the current, the restraining torque increases, and the vector differential current I1 minus I2 arising out of difference in CT ratio is not enough to cause the relay operation. Now, fourth is magnetizing current inrush and transformer while switching. Means inrush of they mean to say inrush of magnetizing current in transformers while switching in. See, when the transformer is connected to the supply, a large, that is 6 to 10 times the full load inrush current takes place. Okay. Now, so we see when the transformer is connected to a supply, a large current means when that's called the inrush of the magnetizing current. That's what is the magnetizing current 6 to 10 times the full load current. See, means when the transformer is connected to supply, basically a large current that is 6 to 10 times the fluid current is in current inrush takes place. That is inrush of the magnetizing transformer while switching. Now, this suddenly causes what happens. See, due to this inrush of the large magnetizing current, this causes operation of differential relay current. This causes the operation of differential relay current inrush takes place. So what will happen? This certainly causes what happens. This certainly causes the operation of differential relay, though there is no fault in the transformer. Now, why the differential operating? Because you see, relay sensing large current. Na? Inrush to magnetism is also when transformer current to supply a large current 6.4 current transformer. So whatever, this is causing the operation of differential relay, even though there is no fault in transformer. Again, to avoid this difficulty, harmonic restraint is provided for the differential relay. Okay, harmonic restraint is whatever differential relay. This relay filters the harmonic component from the inrush current. I to avoid this difficulty, see harmonic restraint is provided for the differential relay. Harmonic restraint. Again, this relay filters the harmonic component from the inrush current and feeds it to the restraining coil. I repeat, to avoid difficulty, harmonic restraint provided assumes avoid this unnecessary mal-operation. The harmonic restraint is provided the differential relay. What happens? That relay filters the harmonic component from the inverse current and feeds it to restraining coil. Now again, the magnetizing, as you know, the magnetizing current contains a large amount of harmonics. So what the restraining relay will do? This will filter harmonic components and will restraining. Or this harmonic content is used for obtaining the restraining torque during switching of the transformer. Next is tap switching. Now again, when I go for tap, you know what is tap switching means? Transformer tap switching. So again, this tap changing, this tap transformer tap changing, you know very well. So this tap changing causes the change in the transformation ratio of the transformer. Thereby, the CT ratios do not match with the new tap settings. That means, as you know very well, I repeat once again. See, with the help of this changing, the transformation ratio of transformer can be changed. Thereby, the CT ratios do not match with the new tap settings, which are resulting in current in the pilot wires even during healthy condition. So, this aspect is taken care by the biased differential relay. Is it clear? So if the CD ratios don't match with new tabs and say result in current in the paired wire, yeah, even in healthy condition, there's the aspect is taken care by the biased differential relay. Now next topic is distance protection. So this was all about differential protection I covered. Another day we are going to study the in detail the impedance relay and all. So let me take your attendance before going to next topic. Third year A, roll number 1 to 10.
Roll number 3. Roll number 6.
Roll number 10.
Sir, roll number 9.
7.
Roll number 8.
Then 11 to 20.
Sir, 7.
Okay,
Roll
7.
number 11.
Sir, roll number 12.
Roll number 19.
14.
15.
13. 13.
14.
चिकने आने के
Roll number
चिकने आने के सर तो गलत दिखा रहा है. रोल नंबर 6 था मेरा. सॉरी सर डिवीजन.
then 21 to 30. Third year A.
21. 21.
25.
29.
28.
30.
Next 31 to 40.
36. 35.
38.
40.
Next 41 to 50.
42.
41. 41.
45.
44.
49. 48.
50.
Next 51 to 60.
56.
54.
50 on 4.
53.
59 sir.
56.
60.
57.
59 sir.
60.
Okay. 61 to 70.
63. 64.
67, sir.
70.
66.
71 to 74.
71.
73.
71, sir.
Sir, roll number 60.
I marked already, na? Then why are you? Bhageshri Parab. Roll number 60, na? Pardon?
Roll number 34.
Okay. Third year B division, roll number 1 to 10.
Roll number 2, sir.
Hmm?
Roll number 2.
Roll number 3 sir. Roll number 7. Roll number 6.
Roll number 10.
8, sir.
Roll number 9 sir.
Then 11 to 20.
18, sir. 17, sir.
13, sir. Roll number 13, sir.
Roll number 16.
Roll number 19.
Roll number 17, sir. 17.
Then 21 to 30.
21, sir.
Roll number 22.
25.
29.
Roll number 20.
20.
27.
22.
28.
Roll number 30.
29.
31 to 40.
23, sir.
35, sir.
39.
34, sir.
Next, roll number 41 to 50.
Sir, 37, 36, sir. 45.
Just 1 minute, please. 1 minute. 37.
36, 36, sir. 37, 36.
41 to 50. Yes.
44.
43, sir. Sir, 48. Sir, 50. 49.
Next, 51 to 60.
Sir, 51. 52, sir. 54, sir. 55, sir. Sir, 56. Sir, roll number 58. Sir, roll number 59. Roll number 60, sir.
Okay. 61 to 70.
66, sir.
65. 64, sir.
67, sir.
8, sir. 69, sir.
70, sir.
Next, 71, 72.
Roll number 71, sir.
Okay. So let us now discuss about the distance protection. There is SS route chapter number 29. Now again, out of that, out of these topics, let me see, somebody is put in chat box. Third year A, roll number 17. Okay. Now again, if you see in previous question papers, it has been asked in the previous question paper, the working principle of the impedance relay. Okay, so first let us try to understand this first. See, basically distance relay, basically they are the double actuating, the distance relay are the double actuating quantity relays. Okay, the distance relay are double actuating quantity relay with one coil energized by the voltage and the other coil energized by the current. And the torque is produced in such a way that when the V by I reduces below a set value, the relay operates. So during a fault on the transmission line, as you know very well, the fault current increases and the voltage at the fault point reduces. Okay, so I'll be to see during a fault on the transmission line, the fault current increases and voltage at fault point reduces. The ratio of V by I is proportional to the location of the CTs and VTs. So again, the voltage at the VT location depends on the distance between the VT and the fault. Okay, so voltage will look depends on distance between the VT and the fault. If the fault is nearer, the measured voltage is less. Okay, so voltage. So the ratio V by is measured middle of the location of the CTs and the PTs. Okay. So voltage at VT location depends on the distance between the VT and the fault. Okay, so if the fault is nearer, the measured voltage is lesser. So if the fault in further, if the fault is far away, then the measured voltage is more. Why I told you, since during the time of when the fault occurs, the voltage at this fault point increases and reduces, and the current increases. So if the fault near hota hai, the measured voltage is nearer, because if the fault is further, the measured voltage is more. Hence, assuming constant, if we assume constant fault resistance, each value of V by I measured from the relay location corresponds to the distance between the relay point and the fault along the line. Hence, such a protection is known as the impedance protection or the distance protection. Now, again, the distance protection is a non unit type protection. The protection zone is not exact. The distance protection is a high speed protection and is simple to apply. It can be used as a primary and the backup protection. Okay, so it can be used in carrier aided distance schemes and auto reclosing scheme. Now again, principle of the RX diagram. Now RX diagram are used in plotting the characteristics of the distance relay. Now again, the three variables V, I and phi are converted into two variable R and X. Okay. So basically, as you know, the impedance Z1 is defined as a ratio of the RMS value of the voltages. The ratio RMS value of the voltages V and I. So Z1 is equal to V1 upon I1. Thus, you can see thus V1 I1 can be converted to RX diagram like this. So this you can see this is a RX diagram where R is on the real axis and X is on the imaginary axis, and Z is what R1 plus JX1, that is called the impedance. Okay, there's a family of the impedance relay or distance relay offer a wide range of characteristics. The basic principle need to be understood and needs clear explanation. The relays which measure plane impedance are known as the impedance relays. The relay which measure plane impedance are known as the impedance relay. Now again, see this is, as you can see over here, this is the RX diagram of the impedance relay. The relay which measures plane impedance are called the impedance relay. So their characteristic on the RX diagram is basically a circle with the center as the origin and radius as Z, that is impedance. Okay. So a bit relays which measure plane impedance Z are called as the Z are called the impedance relay basically. So their characteristic on RS circle centers origin radius as Z, and the relays which measure impedance or the relay which measure impedance but respond to faults on one direction only are called the directional impedance relay. Okay. So I repeat, it means those relay which are measuring impedance but like what they respond to faults in one direction only are called directional impedance relay. Their characteristic on the RX plane is a semicircle on an inclined line. Okay, that is the center or the semicircle center RX diagram. Now again, again this is a RX diagram you can see over here. So these are all about this is all about the RX diagram. Let us look at the theory of the impedance measurement. Now again, the term impedance applies to what resistance plus reactance. So as we know that the ratio of the voltage across the branch, the voltage across the ratio across the branch, the ratio of voltage across the branch to current in the branch gives the impedance of the branch. So V by I is equal to Z, that is equal to R plus JX. The impedance relay operates for certain conditions of ratio V by I, which may be expressed as the impedance. So in next class, we'll continue with this further. So I'll stop over here. Thank you.